It means snail. I think they're maybe meant to look kind of like snail. I don't know, something like a snail. A living snail as opposed to a dead snail, which you know the word for too. Escargot is a dead snail, right? These are living snails, I guess. What these are. Okay. Well, with that in mind, let's turn our attention to some other graphs too. And particularly, we have a couple that I want to highlight today. We'll say something about spirals just for a second at least, and then lemniscates and lines. We should say something about all those things. Can we do that? Okay. I actually don't want to graph this by hand. You feel free to graph this on your calculator though. Before you graph it though, can you just convince yourself, please, in your own mind, take a second to do it, that that's a spiral? Like just try. If you plug in 0 for theta, you get r equals 0, yes? And then as theta increases, as you're increasing theta, r is getting bigger. Isn't that true? You feel it? Okay, go ahead and graph it on the calculator and just confirm that you're not crazy. But that's right. It is a spiral. You think it's a spiral? It is a spiral. Try a window like, I don't know, 0 to, for theta. Yeah, you want to see a lot of the spiral, make that number big, right? Whatever. You can put whatever you like here, right? You can see it go around as many times as you like. Yeah.
As opposed to the way things like honeycombs and prose curves do, because there's not a sine, cosine, tangent, etc.
Yeah, it's a little messier in some
thus
sense.
meaning that every loop around doesn't cause it to reset, rather than continue going up.
Right. Yeah, I mean, the things with the sines and cosines of theta mean that our graphs are always bounded in some way.
This isn't.
This goes out really far as you like. If you graph this on 0 to whatever you like, you'll get a spiral. What happens if you graph this from like negative 4 pi to 4 pi or something? Well, then you could try it. You'll get kind of like 2 spirals on top of each other, going in opposite directions. Yeah. Yeah, mess with your window maybe a little bit. Make sure you're in the right mode too, maybe.
That's most like dying when you try to graph spirals. It just cuts off close to the origin, tries to pull, and at an arbitrary distance.
Then Annabelle, you may also want to check maybe the theta step too, right? But check your theta min and theta max is the first thing I'd ask.
It looks even.
Did you get a nice spiral there? Like I said, if you go from 0 to whatever, you'll get a nice spiral. If you do from like negative 4 pi to 4 pi for your theta min and theta max, you'll get like 2 spirals on top of each other. Does anyone try that? Huh? Do you? Like so? I don't really have anything else to say about spirals. I just thought you should see one. Okay. Let's do a lemniscate. It's weird. It's weird how this is written. Maybe you're welcome if you once we do finally go to put it in the calculator. You might like it solved for r. Do we need maybe we need like a plus or minus here. I don't know. Let's think about that. But as usual, let's just kind of poke this thing and see what happens. If you plug in 0, what do you get? If you plug in, I don't know, pi or 4, what do you get? Plug in some values. Can you sense what this is going to look like? So let's actually start doing that here. If we plug in 0, what do you get? Let's get at least 1 point on this graph. What happens when theta is 0? Yeah. Yeah, did you get 4? Theta is 0? 4. And actually, when theta is 0, we also have 2 things that when squared could give us 16, actually, right? When theta is 0, either negative or positive 4 would work to solve that equation, satisfy that equation. theta is 0. What about pi over 4? Let's try that one next. If theta is pi over 4, what do you get? Is it obvious that that's 0? I just want to, like, we keep asking that question, right? Does this ever hit 0? And the answer here is, I think, a clear yes. Does this ever equal 0? You could solve for it, but we'll just kind of figure it out just now, too. In fact, all the places where we're, like, over 4, pi over 4, 3 pi over 4, are all going to be the places where we're back at the pole. Okay. What else you got? You want to try pi over 2? You going to rain on a parade like that? Just like that, Franklin. You confirm what he said is true, that pi over 2 is kind of like a broken thing. Yeah, if you plug pi over 2 in, you get, on this right side, you get a negative 16. And I don't, without resorting to complex numbers, I don't see how we can take r squared. I don't know anything that 1 squared gives me negative 16. So yeah, certainly we have something, this is a little weird that this is happening. We get an undefined portion of the graph. In fact, it's not just at that value, it's any time that cosine of 2 theta is negative. So that'll be any time between pi over 4 and 3 pi over 4. Those will all be undefined. That's any angle between those. And maybe down here too, right? Anytime the cosine of 2 theta is going to be undefined, is going to be negative, right? But when it's positive, when this is positive, this feels a lot like, well, I don't know. What would, if the squared wasn't here, what would this be? It'd just be a rose curve, right? So I have every reason to think that this here, I'm not sure what's going on with the undefined part, but I have every reason to think that at least on these parts, it just looks like a rose curve. Which makes sense. That's exactly how it would look if this was just like a rose curve and this was like 4 cosine 2 theta or something. It would be kind of similar to that. Except we normally expect to see also a pedal here and here, but they're kind of like, I don't know, imaginary or something. They're just not there. Feel free to graph this now on your calculator if you haven't already tried it here. Try graphing this on your calculator. And watch as it graphs it. It'll actually take some time to process. As it's graphing this, it'll graph this. And then it'll pause. You'll see it's like processing, but not graphing, processing. And then it'll pick up again, okay? The other thing I want to warn you of is when you go to the graphing calculator, we have this picture right, but your graphing calculator often doesn't render the area near the pole correctly. Do you see that yet? Anyone who has it? It's like not coming together properly. Yeah, it kind of gets tired or something. I don't know what happened. But we all are very convinced, aren't we, in our own minds, that this is definitely the way it looks. It definitely does hit the pole. Yours works, Annabelle? Yours is fine. Good. Well, it's one of those new fancy things. Yours looks good too. By the way, this is the symbol that this is the infinity symbol, by the way. Yeah.
Not as numerable.
It evokes a sense of limitlessness, right? Forever looping. Yeah, see, don't trust your calculator. You can only calculate. I cannot do mathematics, right? Okay. Be the thinking person in the room, not your calculator, okay? Are we good with that? I have really nothing more well, actually, I do have one more thing to say about Lemniscates. What happens if this is a sine instead of cosine? It'll be vertical or something? Okay, test whatever hypothesis you have with your calculator or graph by hand. What would it look like if it was sine instead?
Wait, what?
Why would it be? Yeah, that might change your mind about what that should look like. Why should it look? What's going on? What'd you find for those who changed this to a sine on your calculator?
And it requires side to be.
Yeah, it's actually like in the first and third quadrant, kind of, right?
Because 45
So why is that happening? Can you explain? I don't know. Yeah. Because sine. Okay, yeah. Yeah, I mean, it's the same analysis we did with rose curves. You remember, like, on, didn't we have one like that on the warm-up that was like this? Right? Except we're just now missing these two. So we're here. So it's the same kind of analysis as a rose curve, right? Though it still leaves the question in our minds, how would you get this to go up the vertical? Could you make that happen to you somehow? Or better yet, could you rotate this at an arbitrary angle of my choosing? Like say I want you to rotate this by 33 degrees or something. Can you do it? I don't know. It'll be kind of fun. Bonus question, okay. It's not a super hard question, actually. Well, after all those curves, we've been having fun. We got to end this with lines, right? Turns out in polar coordinates, lines are more complicated than curves. It's been fun, right? It's very easy to make curves in polar coordinates. But now we're finally ready. We're emotionally prepared for lines.
Sure.
Do you remember normal form of a line? From just a little while ago? It looks like this. Do you remember this?
Not really.
Can someone remind me what we mean by phi or phi? And what we mean by p for this? It's definitely an angle because it's in Greek, right? And we're taking the cosine of it and stuff. Wait, say it again. Wait, what? Yeah, so the normal is that like segment that connects perpendicularly from the origin to the line. That's called the normal. P is the length of that segment, and phi is the angle that it makes with the positive x-axis. Right? So, in the context we're now working in polar coordinates, it would be interesting to ask what happens if we convert this to polar coordinates. That is, change x to our cosine theta and y to our sine theta. So far, so good. I'm not playing too fast or loose yet, right? Yeah? Just converting that thing we used to use back in the day to polar coordinates. I'm going to factor out the r because it seems natural and move the p over. And then in the set of parentheses there, just stare at that for a second and just tell me like what is it that you see? It's not 1. They don't cancel out. It's something. It's one of the things. When did we have to call on cosine A, cosine B plus sine A, sine B? It's the cosine difference formula, isn't it? So this then is the equation, a very compact form for the equation of a line in polar form. Kind of makes sense that the line in polar form might start with this idea of normal form because it's like, I don't know, all angular and whatnot, right? We're thinking about distances away from the pole and angles away. So that's cool, that's a great way to say it. Where, and then I describe down here below again, as usual, what those two things are. Keep in mind that r and theta are the variables in this equation, right? R and theta are variables. In practice, these are the two things, p and phi, that you're going to be filling in with like a number, right? I say that because like I see a lot of people like when it comes time for the test or something, they like fill in random things. I don't know. R and theta are going to be untouched, right? Those are. By the way, are we supposed to have a quiz this week? Is that what we're supposed to do?
No, we're not.
No, Tuesday? What is it? Someone look at our calendar. It's Friday, right? Yeah.
On Friday? What's happening Friday?
I think we have our first quiz on homeworks 1 through 4, right? The reason I ask is because I think this is on it, right? So it says on your schedule, right? It should say that. Yeah. I just didn't write it up there, but. All right, is that okay in a box? This is just us kind of deriving it. But in the end, this is our formula. It's just real nice equation of a line. Our second equation of a line this year, I guess, right? You didn't think you'd be like learning about lines in pre-calculus, but here we go. So let's graph this together. Let's see if we can figure out what this looks like. Go ahead and like turn to your neighbor and tell them what that's going to be. What is that going to look like? Are you okay with this way of writing it too? I hope so.
that it's at equal 3 pi over 4
Okay, Daisy, take it away. Give me instructions. What do I do? How do I graph this? Well, how about you tell me anything. You like remote desktop? Okay. Tell me anything you know about this graph at all. Do you know anything about it? Yes! It's a line. It is a line. It's not, I mean, I just gave you a slightly different equation for the last previous page. So that is something to recognize it as a line. Can you give me anything more or no? You sure? Really? Come on, Daisy. All right, okay.
The normal is 4.
Ian, I'll call on you another time, man. Okay. Ivy, take us home here. What's going on?
So if you multiply both sides by cosine theta minus 3 pi over 4, it's the rule of one.
True.
So the angle that the normal makes with the x-axis is 3 pi over 4.
So give me instructions on how to draw this.
So
What do I do?
in the direction of 3 pi over 4, go 4 units.
All right, so that's not the line, but that's like the normal to the line.
And then it has to be like this.
I think I can do it. Something like that. Right? So the normal is 4 units in this direction, and I guess that's what we mean by the normal for the line, so I think we're done. By the way, can you just plug a 3 pi over 4 in? And just tell me, please, do you get 4? Okay, good. Reality check. Okay. Good. Can we be done with this one? Okay. I don't have anything else to say about it. I think some of you thought it was more profound than that, but it's not. That's all I have for you. Okay. It is an interesting question to like go back and forth from rectangular to polar or vice versa. Going from polar to rectangular is actually something you've already done though. Polar to rectangular. I made that, some of those problems, those extra 5 problems, I think there was one like that, right? I think so we had one to warm up yesterday or the day before. Where we were converting from polar to rectangular. But it's a little bit tricky to take a line that we already have in rectangular and convert it to polar. The way we developed the polar formula on the previous slide gives us a little bit of insight into how we did it. How did we get to polar form today? We started with normal form, didn't we? So maybe that gives us some insights here. Maybe we could get this in normal form and then put it in polar form, right? I mean, really, won't we be done if we can name P and phi? We can just fill in the blanks. That would be great if we can just find those 2 things. But yeah, we need to do maybe some work on this. This is like almost in normal form, yeah? We know like the cosine of our angle times x minus plus the sine of our angle times y minus p. Right, but this is not the cosine of any angle, is it? 3? No. It can't possibly be right. Remember how we got in on this? On how we convert this to a 1-step process to get us into normal form? Should feel very familiar after our vectors unit too. This whole idea. We divide by something. What is it, Matthew? Yeah, if you divide this equation by these 2, take these 2 coefficients and does this ring a bell? Right? Again, the reason I said that should feel familiar is because we've done this now in a couple different contexts, right? We did this with normal form, we did this with like linear combinations of sine and cosine. We just did this process recently when we were trying to find unit vectors too, right? This is like equivalent to when I ask you, hey, I have a vector 3, -1, find the unit vector in the same direction. You're like, I think I just need to divide by the square root of 3 squared plus 1 squared, right? The same thing. I'm just trying to create something that's like on the unit circle kind of, right? Anyway, so the point is, I think we have it in normal form now. 3 over root 10 x minus 1 over root 10. Y minus 1 over root 10. So do we know what P is right away? What is it? 1 over root 10. Phi is not obvious, and we are going to, I think, need to reach for our calculators, but we do know what the cosine of phi and the sine of phi are. So can you, someone, help me out here, figure out what phi is? Because then we'll be done. Anybody else on the case? I guess I'll say it's approximately something. I don't know. What quadrant is it supposed to be in? Yeah, it should be quadrant 4, right? Negative 3.2 radians. Do you like radians? Is that what we like?
No.
What do you?
Degrees.
You like degrees better?
Negative 18.3.
All right. Well, whichever you like is fine. It didn't specify, so whatever. Negative 18.3 degrees. Okay. So what's our equation supposed to be? R cosine of theta minus that, how about plus maybe 18.4 degrees equals 1 over root 10. By the way, let's just do a little reality check. Does that feel right too? The graph of y equals 3x minus 1 has this flavor, doesn't it? Isn't that right? This is from algebra 1. Is that what this says too? Tilt down 18.4 degrees and then walk a very short distance of 1 over root 10 away and then draw your line. I'm not completely sure, but it does seem very, very likely that we're right. It seems reasonable, right? All right, just a word to the wise here. The homework tonight is there's like 2 or 3 book problems on Lemniscate and stuff or something, and then this worksheet online. Your book doesn't have a lot about lines, so there you go. There you go. That's the homework. Someone tell Franklin what's wrong. Okay, bye everybody. Homework 4 tonight. See you tomorrow.